Welcome to Wireless Future. I'm Emil Björnsson, and as always, I have Erik Larsson on the line. How are you today?
Oh, hello, Emil. I'm fine. How are you?
I'm great. Happy New Year, by the way.
Oh, Happy New Year. So it's great to start this year off with another episode of the podcast, and I think it's today's episode 24. Is that right, Emil?
Yeah, that's right. And I had a brief opportunity last year to travel and go to a conference. And then I met some of the listeners, which is a great opportunity to get. Unfortunately, it seems for the moment that we'll be taking some time before we really have physical conferences again. But for this episode, we have at least gathered some questions that we have received from our listeners. So we were planning to answer them. So it's great to actually get this feedback from everyone who is actually out there and listening.
Yes, much appreciated. I mean, thanks to the audience for all the feedback and questions that we've been receiving. And I think today during the Q&A we'll be able to address a subset of the questions that we have received. So
definitely. So we have selected 10 questions. We might have reformulated slightly the questions, but I believe the people who ask them will actually recognize precisely the question. So I hope people will be satisfied with our answers.
Absolutely. So you want to kick me soft, Emil?
Yeah. Would you like to ask me the first question, by the way?
Absolutely. So I'll, the first question relates to let's say technological laws of our laws of how technology seems to evolve or has evolved in the past, right? So there's first this Moore's law that states that the numbers of transistors that you can squeeze into to a circuit doubles every other year or every 2 years. And then there's Edholm's law that states that the data rates in the different categories of telecommunications, there is wireless and wired and nomadic, that is doubles every 18 months. And the question is now, what is our prediction? I mean, do these laws, to start with, do they hold? And at what point will they be broken? And which one of them will be broken first? So do you, Emily, want to have a go on this one?
Yeah, so that's a complicated question, of course, to predict. So both of these laws are sort of empirical. People are looking at data of how the transistors are increasing in numbers per square unit of space, or when the data traffic is increasing, how quickly is it doing, and then they try to make predictions. And I think it's fair to say that we have seen an exponential increase, which means sort of a percentage increase every year that is stable. But exactly what percentage that is to some extent the question here. So I think Phil Edholm at Nortel, who was giving the name to this Edholm law, I think originally he was saying that, or noticing that we see this traffic increase, or the peak rates are increasing in all different types of technologies in an exponential pace. And then people started to look at that data. I'm not sure if he did it himself or not, and were then finding this doubling every 18 months. And doubling every 18 months, that's like 60% per year. So I tried to look at the data and see if that still is holding up. And if you look at the mobile data traffic, for example, in 4G and 5G networks, then in the beginning of the 4G era, we were even seeing a doubling every year, which is more than this law. And I think that was also why people started to talk about that, 5G needs to be 1,000 times more traffic than 4G because of the doubling every year that turns into that over 10 years' time. But then if you look at the data, the growth rate is becoming slower. I think it was this 60% for a few years ago, and then nowadays it's more predicted to be 25 to 35%, and it's increasing faster in the developing part of the world naturally. So I think that in the mobile telecom, this was really, now we are switching to using our mobile phones for internet connections, and then that is increasing quickly, and then it converges to something. And what will it converge to? Well, if you look at Cisco data for things for internet traffic in general, it seems to be rather stable now, around 25, maybe 30% increase per year. So I think that is what we are really converging to, that people are not caring about if they use fixed internet or the mobile phones, and then the general traffic growth of the internet will then be the one used in all of these things. So there, I think my conclusion is really that the Edholm law have already died a few years ago, perhaps. Then there is, by the way, also the Cooper's law. Martin Cooper from Motorola, who was noticing in the 90s that he was claiming a doubling in wireless traffic every 2.5 years, which is like 30%. And we are closer to that, I believe. So maybe that law isn't dead yet.
Of course, I mean, it's hard to make predictions about sort of things for the future, right? I mean, so my understanding is that it took longer than what the industry thought for mobile broadband to take off. But once it took off, it really took off, right? And we don't know about the future. I mean, for certain, mobile broadband is one of the main applications. But we'll also be seeing like all these machine-to-machine and AI and machine learning applications that would require like vast amounts of data transfer, and that might not have taken off yet. And we don't really know when it will. I mean, it's almost certain that at some point it will, but when it will happen and how fast it will happen. Will it like double every year or quadruple or tenfold or some percentage? It's like almost impossible, I think, to predict. So that's like my view on the question.
And we were discussing this slightly with Magnus Frodig from Ericsson last year, and I think his point of view was that we might be in a transition phase now when we are waiting for the next big thing, which might be VR or applications, and then the traffic might once again go up to these numbers. So I think the future will tell there.
So how about the Moore's law then? The question here related to Edholm's law and Moore's law, and to what extent they're like compatible, I suppose. So
I think Gordon Moore was already in 65 or something like that. He was noticing these things, and then it has been sort of a self-fulfilling prophecy that we should make sure that we can double the number of transistors per unit area in the chips every 2 years. And I think nowadays you can find a number of different news articles claiming that Moore's law is dead. But I think it really boils down to how do we really define these things? Because if it's about that we're only caring about that we should double the number of transistors, then we are approaching the end of that development if we haven't already done it, because when it's only a few atoms sized transistors, you can't shrink it more, right?
But there's an absolute limit at some point, obviously.
Exactly. But if you rather is interpreting it as, can we continue doubling the performance of chips every 2 years when the chip is of the same size, there we have actually seen good improvements in recent years with system over chip kind of things. So even if we are not shrinking the size of transistors, the efficiency of the implementations is still following this trend.
So, and it's not only a matter of like densifying and packing more transistors onto the chip, right? It's also a matter of like implementing large-scale DVF, dynamic voltage and frequency scaling technology, for example, so that within the same chip you can have different zones where you control the speed of independently, and therefore the power consumption and so forth. So I think that DVFS technology and also massive parallelism in how you do computations and how you deploy, in like a mobile device, you might just have a single chip, but in data centers you'll have many of them, right? And then it becomes a matter of how do you distribute the computations across these circuits in order to minimize like power consumption. So it's not only the density of the integration on a piece of silicon that matters here in the end.
So if I should wrap up my long answer here, I would say that it's debatable now if Moore's law is starting to die or not, if we should just reinterpret how it is. So that one still seems to be living, while the Edholm's law, I personally think that it died a few years ago. and maybe we should view more Cooper's law as the living version there.
Yeah, and let's remember, I mean, fitting and extrapolating exponential functions is very difficult and dangerous.
Yeah,
So.
yeah, definitely. But I think for the time being, we will at least see exponential increases in both of these cases. Then what the exact pace is a different thing. Maybe it's just switching the growth rate, but it's still exponential. Okay, should we take a second question?
Absolutely.
So I have a question for you then. As more antennas, wider bandwidth and higher frequency are utilized, it's seen that communication and sensing will be integrated. What's your opinion on this area? What problems are worth tackling in the next few years?
Yeah, sure. So, I mean, to start with, obviously, RF signals can be used for communications, right? And they can be used for sensing, which both are like established technologies. I mean, sensing means radar essentially, right? And communications is what we have in the mobile systems. So now, speaking of integrated communication and sensing, I think there are a few different things that people refer to. One is that we could use equipment nominally designed for communications to also do sensing. For example, a Wi-Fi access point could sense the environment, check essentially whether the channel impulse response varies over time or has changed in a certain way, and draw conclusions then on what's going on in the room where it's deployed. That's already a technology, using Wi-Fi for sensing, right? I mean, there are methods you can use to detect whether someone has fallen on the floor or how many people are moving in the room and so forth. I think it's a greatly exciting and potentially highly useful technology indeed. And I also think that scaling that up, I mean, now using like massive MIMO arrays to do this sensing, well, with a single antenna, we have a lot of data, right? Over 20 megahertz bandwidth, you have like 20 million samples a second you can play with. And now if you have, on top of that, or in addition to that, if you have 100 antennas, you have like 100 times more baseband data, which gives you, in addition to temporal and frequency resolution, also gives you spatial resolution. So I think there are great opportunities there for both for new algorithm development and also for development of new applications. Now, speaking of integrated sensing and communications, one could think of course, using communication signals for the sensing, like getting the sensing result as a byproduct of the communications, rather than sending a signal that's tailored for the sensing. Particularly in a radar signal, essentially you could send a data packet and then use that waveform for sensing. Certainly, I mean, if bandwidth scarcity is an issue, I can see that could be useful. Definitely, I mean, you could get the sensing result for free as a byproduct or as a bonus of your communications link. So absolutely, I think it's an exciting area with very good prospect for new algorithms, new applications, and useful applications. Another aspect of this is question, I think, relates to radar systems, and a good example, I think, is radars on board vehicles, because I've heard a case being made that, I mean, we have for communications, we have very good standards, right? Ways of getting along, and like how to buy pieces of a spectrum and get exclusive license to use that piece, and then how to get along within unlicensed spectrum, for example, like with Wi-Fi and so forth. But I've heard a case being made that for radars on board vehicles, there aren't like any good standards for how a radar on a Mercedes should coexist with a radar on a Toyota or some other car, and then it's very possible that the automotive industry here could borrow or be inspired or rely on the telecommunications industry and the efforts and the, say, wisdom and experience learned there in the standardization in order to develop ways that radar systems could coexist in the same spectrum. Because at some point, if we start deploying radars on every vehicle and maybe other types of radar sensors out there, they would have to get along in the same piece of spectrum, right? And certainly one could think of, like, again, they're starting off from the radar and then using the radar signals also for communications. So again, I think integrating sensing and communications and using the same signals for both purposes would be meaningful mostly if we really have a shortage of spectrum, so that we can't afford like sending a separate probing signal for the radar and then sending a communication signal for the data transfer. So certainly I think it's an exciting, let's say, research field with many potential useful applications for the future.
Yeah, no, that is my impression as well, that this is really one of the interesting topics to explore more now when people are talking about 6G. What kind of things would we have to bring with us when standardizing that type of technology in order for making sure that it actually works out well? Because I think the hope is sort of that we should be able to then use all the base stations that will anyway be deployed for these purposes. So if they are prepared there, then as you were
I mean the hardware, the equipment is already there, right? So think of it, if you have as a possible maybe futuristic application, but if you have a macro cell massive MIMO base station up there with hundreds of antennas that are used for all this multiplexing of traffic and all that, and then you could, this is a bonus, use this base station to recognize activity that's going on in the area or counter traffic on the highway or something. I mean, that would be it's just an exciting prospect indeed.
Yeah. So I think for people who have some previous expertise in MIMO or in localization or millimeter wave areas, I think this is a good future research topic to work within, where you sort of build on your knowledge you already have, but also do something new that haven't been explored as much.
It should be. Absolutely, it should be. Yeah. So third question that we've received, if you, Emil, want to have a go at that, and it relates to 5G networks and specifically private and local 5G networks, and where we stand with that and how soon that we are going to see these private and local 5G networks being deployed on a larger scale.
Yeah, this is a good question. So I think this is to a large extent not a technology question anymore. There are hardware that you can utilize for 5G, obviously, but more of a regulatory aspect. But in Sweden, for example, like a month ago, there were a decision from our regulatory body saying that now people can apply for local licenses. You can get like up to 40 megahertz in the 3.8 gigahertz band. You can get, there's like 850 megahertz in the 25 gigahertz band. I guess one can get 400 out of those per building. Building owners can apply for this now, and it seems like the spectrum are very affordable. For a few $100, you will get a license for most of the spectrum there. So I think then the main question... So
$100 per hertz, I suppose?
No, I think it was...
Range here?
I think the price range was a bit like $50 for 10 megahertz in the 3 gigahertz band there, and then it was half of that price for, I don't remember exactly the numbers there, but it was cheaper in the millimeter wave where there's also more spectrum.
Yeah, but I suppose this depends on how large geographical area that you want to use
so this
the license for.
was like one building.
Oh, one building. Okay.
Yeah,
so it's not it's per building. It's not like per square kilometer or something. So.
No. So in Sweden, this was connected to a building. So sort of in your application, you need to mention which building it is. So I think we will then see next year these kind of deployments. Then I think many are pondering on what will you use it for. I was talking for people at a premium hotel chain in Sweden that seemed to be interested in trying it out. So what would be the benefits compared to Wi-Fi? Well, you can probably have more predictable latency, more controllable data rates and things like that. People will not destroy it with putting up a Wi-Fi network in the room. But in which situation do you really want to pay for this? I think the future will tell.
Yeah, I mean, in the end, Wi-Fi works pretty well, right? Properly deployed and installed, it's a pretty good solution indoors. So So these licenses, I mean, how do you actually buy them? So are they like at fixed price? So you go to Media Markt and buy like a gift card, $50 of Spectrum for Christmas?
So in Sweden, you fill in a form and submit it to the regulatory body here. But I'm sure it can be different countries, and also in Sweden, it's not all parts of Sweden where you are allowed to get it right now. Some municipalities have dropped out, some have sensitive equipment. They don't want people to go out and deploy things themselves.
Wow. Oh.
Yeah, but I believe that the most important thing might be factories or mines or construction sites and these type of things where you hopefully will have robots that should be connected and maybe use 5G for that.
Right, where you really need to or want to make sure that there is no interference from anyone. I mean, you're the only one who are allowed to transmit actually in that spectrum that you bought.
Yeah, exactly. Okay, I have another question for you. One of the claimed key candidate technologies for 6G is RIS, or Reconfigurable Intelligent Surfaces. Do you think RIS will be a key enabler of 6G? And the question is also adding here, 2 key motivations behind RIS is low cost and energy. Until now, are these claims justified or not?
Yeah, good question. I mean, so first, is it RIS or RISE or RIS, or how to actually say this? Some people say IRS, I think, but RIS or RISE seems to be more common.
I think we are converging towards that name. And it was a bit like Massive MIMO also had many names in the beginning, and then people converged towards that name.
Yeah, right. So maybe we'll just say RIS then for a discussion here. I think you can get different answers depending on whom you ask here, and my stand is that I'm rather hesitant to RIS being, even a key technology in 6G, let alone having much of actual real commercial potential on a large scale. So, I mean, let's see if we can steelman the argument for why RIS would be a key technology in 6G, right? So there is this case being made that RIS could be used to improve coverage, which I think is factually correct. I mean, it's certainly be a lot of fun to participate in, like building prototypes and testing this technology. And I'm not denying the fact that there are also like bottomless with research problems, right? That one can and people have been written a lot of papers. Indeed, it's a very popular like research topic in academia, but. So now this argument that it could be used to improve coverage. I mean, for example, you could like put up somewhere in your home, you could put on the wall something that looks like a painting, but is actually a reflecting intelligent surface. And it would have to start with to be quite large to provide any gain, right? And it would have to be powered in some way. So you need either a battery or you'd need to connect it to a power outlet. And then I don't think it's feasible really technically to make RIS out of energy harvesting technology. So you would have to power it somehow. Once you power it, then I feel like, okay, so now you put this up and you got to make an effort to that it's not ugly, right? I mean, it has to look like a piece of art or something. Otherwise, there's just no way I would put it up there. And then if you do this, it'll take up a lot of space. I mean, and the same space, and given that you anyway, put connected to the grid through a power outlet, and why not put a small access point there? I mean, small Wi-Fi access point, a small repeater, or one of these is TP-Link, or what's the brand name for this Wi-Fi repeaters, and or even a small MIMO like array or something, right? And outdoors, I mean, you could certainly think of like in a mega city, right, with skyscrapers to cover the facade of the skyscraper with a RIS that would be many square meters large. Then it's kind of a fascinating prospect to do it. But again, I mean, my impression has been that even just the installation costs and the site costs for conventional base station and access points is just humongous, right? And then now saying we put in a RIS up there, which is tens of square meters large, then well, powering it might not be a big deal, but actually installing it and like, well, maybe it'll be beautiful. Maybe it'll look like some golden kind of decoration, or maybe it could be integrated into some kind of neon light flashing, ad billboards, or who knows. But I still find it like hard to make the case. Besides, my understanding is that in big cities, I mean, we have a capacity problem, right? And if we have a capacity problem, then certainly we could have a coverage problem also, but we do have a capacity problem. That's why massive MIMO at lower bands already has succeeded commercially in deployments in big cities. And then given that, why don't you just install another massive MIMO base station there? I mean, I think we share this vision, you and me, Emil, that the way massive MIMO base station should look like, right? Like a big flat screen TV, more or less. And, you could make it very large. You could distribute the antennas over the facade of this building. And I think we discussed that. Didn't we talk about that in some previous episode of the podcast? Or if not, we should, I mean, at some point in the future. But the idea of building like a distributed massive MIMO array, which is many square meters large and could cover, the facade of a skyscraper. So I think my stand on, so the question was whether RIS is a key technology in 6G. Well, certainly it's kind of fascinating technology, right? And it's just maybe my personal take on it is I'm ambivalent, and I have a bit hard to see that there would be major commercial use cases for it. I can see that using RIS sort of technology, or rather metasurface technology, to build MIMO transmitters could be meaningful at very high carrier frequencies especially. So rather than building a coherent MIMO array, you have like a single antenna transmitter, and then you have this reflecting metasurface nearby that you use to control how the beam is shaped, right? But that's a little different.
Yeah, there is already commercial hardware.
Yeah, and that I fully support. I mean, that's more like a way of building a beam steering. Well, it's not really MIMO, right? It's like more of a phase array kind of beam steering transmitter. So certainly, but RIS for coverage and capacity enhancement. So again, I mean, it's hard to predict the future. I might be wrong, but my assessment, let's say, of the situation is that it's hard to find like a clear case that this really be commercially even viable on large scale in the future. What do you think, Emil?
Yeah, so I think that the lowest hanging fruit that we would be able to use something like this for is to try to remove some coverage holes where it feels unnecessary to put up new base stations just for that purpose. But then a coverage hole is typically a fixed location, an area. So the reconfigurability might not really be needed there. Maybe we could put up some clever surfaces that are not reconfigured and always reflect the signals around the corner or into a particular coverage hole. So I think I've heard telecom operators showing interest in those use cases, but whether we need it real-time reconfigurable and therefore having an energy consumption, I don't know. It's really this configurability.
Yeah, that's a good point. I mean, you got to separate on one hand the reflecting surface kind of technology, and on the other hand the whether the surface is intelligent and can adapt instantaneously, right? So yeah, maybe. Yeah. All right. Great. So maybe we should move on here through the list of questions. And if you want to go on the next one. So the next one is on large apertures in massive MIMO, and specifically how to use optimal precoding and combining methods to eliminate interference when the dimensions of the channel matrix increases, whether we can manage the complexity of the processing. So I guess this refers to like build larger and larger antenna arrays, maybe distributed even, right, with MIMO, and at some point you will run into a computational problem because of just the sheer amount of baseband data and samples that have to be processed.
Yes. So if we go back to the initial works by Tomer Zeta for massive MIMO kind of research, which was really about really large apertures going to the infinity or something like that, then he was advocating a lot for using the simplest kind of processing, like maximum ratio processing where you don't need to invert any matrices or anything. You don't actively try to get rid of interference by processing your data signal. You just see that, well, we have so many channel dimensions so that the users will automatically become distinguishable. So if we build these large surfaces, we could hope for doing that. We have probably seen with the sized arrays that we have today that we can get big gains by using MMSE zero forcing kind of processing method, and it's feasible to implement. But if the complexity of doing something like that is growing linearly with the number of antennas and quadratically with the number of users, then eventually it might be too heavy. So what do we do? I think that is really what it boils down to. And I think one can look for something in between, just ignoring interference with maximum ratio and hope that the channel is automatically taking care of it, or doing full-blown MMSE. So we had some work that we called polynomial expansion precoding, where we took the matrix inverse, we expanded it as a polynomial with a few terms. It's like a Taylor approximation of an inverse, and then we apply that. It doesn't necessarily reduce the number of operations that much, but it gets rid of an inverse, which it might be easier to implement. But I think what one should do to make this work well is to take all of your dimensions you're having, trying to spatially filter the signal somehow. From which dimensions do we get signals, from which one do we not? Try to figure out in which dimensions are there multiple signals from different users, and apply some kind of interference interference suppression in those dimensions, not in the other one. So be a bit more clever using some kind of hierarchical implementations of interference mitigation.
Yeah, absolutely. I mean, and again, there are great opportunities, I think, for further algorithm development in that regard. So it's a good question. Yeah.
And I think when we were briefly talking about this near and far field kind of things, we were also mentioning that some of the things that people are analyzing is just for an array of a certain geometry, what is a set of beams going in different directions? What are the dimensions? For a uniform linear array, we have this discrete Fourier transform that happens to point out signals going in a orthogonal set of directions. And can we, for other type of arrays, figure that out from the beginning? Because then we know what spatial filtering will be. We should go through those different dimensions, and then we don't need to compute eigenvalue decompositions. That would be super complicated to figure out where the signal is. We can just filter in different ways. Okay, I have a question for you, and it's about machine learning. Do you think it can be a game changer in the coming year for 6G development? And the person is adding, I've heard people work in the industry saying that this is just a matter of citations that people are considering because machine learning is not used for industrial research and development.
Yeah, so whether machine learning can be a game changer for 6G. So let me first say that I'm enormously fascinated and impressed by modern machine learning algorithms and what they can do. I mean, particularly in computer vision, right? I mean, recognizing objects and videos and images and in natural language processing and so forth. It's just amazing, I think, this development we've seen over the last, maybe 10 years, I think it's... This really happened and continues to happen, by the way. I mean, it's just highly fascinating. Now, for 6G, certainly, machine learning, which means a lot of things, right? I mean, a lot of people associate, it seems, machine learning with only convolutional neural networks or deep learning and so forth. But it's not really accurate. I mean, machine learning is a lot of things, right? Some of which have been around for a very long time, like even just fitting a non-linear function or spline or to data points is in a way it's machine learning, right? Like regression problems. And certainly machine learning is an important tool in the toolbox, no question. And there are cases where it's extremely powerful to use in let's say in COM theory applications, where I think we discussed this in a previous episode, right? When we don't have maybe accurate physical models, model something like user mobility or something, and you might not use, or if you attempt to model user mobility, you might not start off with Newton mechanics and kind of like a human looks like this, right? You have a head and you have a body and so forth. I'm not saying it's completely infeasible, but it seems like a use case where, you know, this postulating some, well, model that you can train with a neural network seems like a very useful approach, and indeed I think it is. Now, whether it's a game changer, probably not. I mean, in the end, I mean, wireless comms is limited by physics, right? In the end, it's like, well, speed of light limits the coherence of the channel, which limits how fast we can obtain channel state information and how many, you know, users we can multiplex with a MIMO array and so forth. So I think probably not the game changer, but definitely a useful tool in the toolbox. And then there is also, I think, another aspect that deserves to be mentioned here, namely that, so there is this argument that there is now hardware becoming available off the shelf that can implement certain machine learning, or air quotes, machine learning algorithms, neural networks in particular, right? And we have all these GPUs and that like family of hardware. And therefore, given that we have this hardware available off the shelf, then that it would be meaningful to abandon like classical algorithms and rather use algorithms that can run efficiently on this particular hardware platforms. Well, I can certainly see that if you work for a company that manufactures this sort of hardware, they want to make the case for that. But you know, in the end, I think we have to be more visionary here too, right? I think there's no question that an ASIC designed for a specific task is always going to be more, or let's say a well-designed ASIC. Where an ASIC well-designed for a specific task is always going to be more efficient than any available off-the-shelf hardware platform. And today, it's very difficult and expensive to develop ASICs, right? I mean, you put in like thousands of man hours, and then manufacturing, you need like produce many of them even for the initial costs to set up costs in the manufacturing process to pay off. But I'm not sure there is anything fundamentally that, I mean, means that this has to be that way, right? I mean, if we think of a future, 25 years down the road, who says that, or what says that we could not do rapid prototyping with ASICs? Like, you have your simulation code in Python or C++ or some language in your PC, and you just hit enter, and then you wait overnight, or doesn't really matter. I mean, how, but it could be some AI algorithm in the backend that does the job and translates your code into highly efficient VHDL, and then you hit enter again, and it's sent off for a manufacturer, and you get your chip back in a few days. Just like the development in metal and plastic manufacture, right? To build like prototype of a piece of plastics used to be that you have to either use milling or you have to build a mold, and then you like mold the plastics. But now with 3D printing technology, you can do it in your basement directly from the CAD software. And we are not there yet, obviously, with hardware and ASICs, right? But it's not clear to me that we couldn't be heading there, and I think that's another potential development that we ought to talk about. That would also be very exciting. And so, anyway, that was like the comments, maybe tangential to the actual question here, but I felt it was worth making. So, what do you think, Emil?
I think the question is also a bit negative in the tone. I think that the industry are using machine learning, but then actually throwing out existing algorithms and replace them entirely with machine learning, that might be far-fetched. But if you can tune some parameters which people did manually before, and now you use machine learning, well, then if you get 5% improvement in every part of the protocol that you're having, then maybe that adds up to something large in the end, and that is how we should view the improvements. So.
Yeah, absolutely. I mean, and as you said, we are already, and we have been also, depending on how you define machine learning, we've been using it for a very long time, right? So, so it's there, and it's a highly useful and important tool in the toolbox. Whether it's a game changer for 6G, it's a different story.
So
yeah,
you have a question for me?
I do, indeed. So I think we're at number 7 in the list here, and the next one is on dynamic spectrum sharing, and what role could that play in 5G, as opposed to maybe question should be like 5G and beyond, or even 6G, right?
So dynamic spectrum sharing could mean many different things, generally speaking, but in 5G I think it have a particular meaning. So there are products now from the big vendors that are doing these things, and I think the point there is that if you deploy a 5G base station, it should also be able to run 4G in parallel. And with that, it really means that at every millisecond, it monitors the traffic in the cell and determines, do I have 4G or 5G mobile phones there? And then it either transmit 4G or 5G signals depending on what users are out there. So why would that be of interest? Well, if one of the issues is that, okay, you need to deploy new hardware, should we find new sites, new locations to put things up? No, you can take down your 4G equipment, replace it with one that can do 4G and 5G at the same time, and then you are only need one piece of equipment, and you are maybe starting to reuse slowly your 4G spectrum for 5G as well.
Mm-hmm. Yeah, so is cognitive radio coming back then? I mean, because this dynamic spectrum sharing is closely connected to cognitive radio, right? They used to be like popular in cycles or waves, I think. Like, was it like early 2000? Then it came back like 10 years later, and then it was like almost dead for a decade, and maybe it's now getting like hot again.
Yeah, I suppose here it's not really about cognitive radio in the sense that someone owns the spectrum and someone else is allowed to use it if they don't interfere, but it's more that the one who is owning the spectrum can decide what to do with it, what radio interface to utilize. And if you read sort of the documents about how the big vendors are recommending operators to deploy 5G, it's sort of about first deploy massive MIMO in the mid-band. Next step, you might either go for millimeter wave, or you might go back to your 4G base stations that you have in lower bands and replace them with this kind of equipment that can do both 4G and 5G. And in that way you get 5G coverage everywhere. Then to what extent you benefit in terms of performance there, for the moment, maybe not, but once you have a 5G core network so you can do ultra reliable communication and things like this, well, then this is a good way of sort of slowly push people over to 5G and let 5G terminals get 5G services while not having to remove 4G service.
Yeah. Wow. Okay.
Okay, so I have a next question for you. It's a person who would like to know more about this research direction that we were alluding to earlier about sort of convergence of channel and Maxwell theories. What are the current limitations? What are the possible outcomes of this, and what does it really mean?
So convergence of Maxwell and Shannon theories.
Yeah.
I think we did touch maybe that term in some previous episode. Emil, was it the one where we spoke with Tom Marcetta?
I think we mentioned it there. We might have mentioned it in the near-far field case. I'm not entirely sure, but it's usually mentioned in those kind of situations, I believe.
Yeah, I think this is a tough call, right? I mean, Shannon theory and Maxwell, let's say, theory are two rather distinct and different, fields or theories. So then now what I think is important here, what we should do is that when we use Shannon theory, they were aware of the underlying physics, which is ultimately governed by Maxwell's equations, right? And there are certainly cases where this becomes very important. So I think one issue here is that a lot of folks in comms theory and maybe information theory, signal processing, these communities tend to sometimes over-rely on simplified models of the electromagnetics. And sometimes this is just fine. sometimes we gotta be careful, right? I mean, mutual coupling might be the most important example to highlight here. The fact that if you have antennas in an array and they are widely separated by like at least half a wavelength or more, then well, coupling can be maybe not completely ignored, but it's a minor effect in any case. But once the antenna spacing creeps below half a wavelength, then coupling quickly becomes the dominant physical phenomenon. And then things that we're like used to from the comms and IT papers, where we work with models where we get this antenna array and we say that the power is equal to the norm square of the signal vector. Well, that just completely breaks down, right? So we got to be very careful there, and think in that respect, understanding Maxwell's equation and using relevant and accurate models for the electromagnetics is immensely important when we develop our signal processing and comm theoretic algorithms. No question. I mean, this is
yeah, and even without mutual coupling, if it wouldn't have been there, there is also sort of, if you sample things, oversample things over the spatial dimensions, perhaps, and then you don't get more information.
I mean, but certainly, but the question is when the approximations that we tend to make of the physical world when we work on our signal processing algorithms, when do they become really critically inaccurate? And I think coupling is the best example of when something really breaks down. I mean, you put antennas closer and have a wavelength, and just stop it, right? Unless you model the electromagnetics properly, which requires more or less going back to the wave equation and really understanding what's going on there. Another example, I think, is polarization, which is ignored in a lot of the comm theoretic also papers. But in many cases, I mean, as long as we are in a regime where coupling is a minor effect and can be more or less safely ignored, then polarization in the end often tends to just give you a factor of 2 in terms of degrees of freedom and capacity and so forth. But certainly, I mean, accurate physical models are important to use, I think. So I'm very supportive of, and in fact, I think there is the danger here that, well, we might be educating engineers who are extremely skilled at manipulating matrix algebra and computing Shannon theoretic capacity expressions and so forth, but haven't studied Maxwell's equations closely enough, and that's something I believe as educators we should maybe address.
Yeah. So I think for listeners who really want to dig into this, which is how to go into any type of details in a discussion like this, I know there is a book on wave information theory by Fraschetti that might be a first reading.
It's a very nice book indeed, or even just, I mean, reading the electromagnetics textbook from college could be a good idea. Yes. Or an antenna theory book for that matter. Yeah. Great. So did we answer the question? How do Shannon and Maxwell theories can converge? Well, again, I don't know whether it really will converge, but I think the answer here is to, learn both, right? And then when using Shannon theory, then be acutely aware of the underlying physics and electromagnetics, which is ultimately governed by the Maxwell equations. So.
Yeah, and if each of these development in each of these areas are usually considering simplified assumptions regarding what is done in the other field, then there might be something there in between that can be modeled more in detail, and for it will enable us to build more realistic or more advanced systems in the future. But exactly what it becomes, I think it's a bit open.
Mm-hmm. Yeah, of course. I mean, there's also the aspect of, there is an operating regime. I mean, referring back to coupling, there's also an operating regime where coupling is the dominant mode of operation or dominant effect that we want to exploit, right? Like, for example, in near field inductive power transfer. But that's not really maybe at least it's not a pure communication problem. So then we are more in the regime where we we work with Maxwell's equations, and then, well, it's possible we build this inductive coupling link that we can also transfer some information, and then we might need a little bit of Shannon theory to for that to be useful. So, all right, great. So maybe we should move on in the list. I think question number 9 here is for you, Emil. Will side link or device-to-device communication become a major component in future wireless systems?
And then the question is also, maybe it already is. If we consider then device-to-device communication, it's really about two sort of user devices in some sense that are communicating directly with each other with no base station or access point or anything this in between, and because they're in close proximity to each other, and we are using this with Bluetooth all the time between two devices, and there is also the Wi-Fi Direct, where you sort of use Wi-Fi between two devices. So whenever I'm on the train and I connect my phone to my laptop to get internet access, then it's a Wi-Fi Direct, I suppose, that is utilized there. I believe here the question is really about using license spectrum for the things that you have in 5G, for example. And there were 10 years ago a lot of research around device-to-device communications, and the idea that, well, if two devices are close to each other, and instead of communicating via the base station in 2 hops, it will be more efficient if they can just communicate directly with each other. The problem is then, of course, that you want the network to control this. Otherwise, the entire point of having licensed spectrum becomes destroyed, because you're not controlling the interference and latencies and everything in the network. You can definitely do that. What would be the reason to not use Wi-Fi Direct? Well, once again, latency, you can guarantee something around rates and things like that. So when will that be used? I think when people were doing research in the beginning on device-to-device, they talked about, there will be some kind of entertainment systems or things like that. Maybe in those cases Wi-Fi Direct works well. I think right now the core use case might be connected vehicles or connected robots or things like this. So when ultra-reliable communication will hopefully be a thing in the coming years, then having vehicles directly talk to each other under the control of a cell tower, that might be a big thing. So side link for connected vehicles, connected robots, and things like that.
And latency is a major issue as well, right? But
and
maybe
potentially,
it's harder to see. I mean, it might be harder to see like why cell phones or smartphones would communicate in device-to-device mode to one another when you're out on the street. I mean, so
but there are some emerging use cases where latency is the big thing, and in those cases it's still on the table. It's not the technology, so it might be a big thing 5 years from now. Okay, I have a last question for you. Will full duplex radios be adopted in wireless communication?
Full duplex, wow. Okay, so full duplex means a transceiver that can the same frequency band receive and transmit simultaneously, right? So if you have like an antenna connected to some circuitry, then one way, at least, of building a full duplex transceiver is to have a circulator, and that isolates the outbound wave from the inbound wave and separates them like into different branches in the circuitry. So, I mean, theoretically, you could argue that, I mean, if you can transmit and receive at the same time, then you could gain like a factor of 2 in capacity, right? Which I think is only part of the truth, because number one, we need to think carefully about how we define power constraints here. If we take turns, like in time division duplexing, then is the power constraint on the peak, or is it on the average, and so forth? And also we need to think carefully about what happens to interference and all that. So in the end, it might not be this factor of 2. But one could think of like other gains that full duplex brings with it. For example, if you were able to measure uplink pilot simultaneously as you do your downlink transmission with a MIMO array, then you could gain in in latency between the point where you estimate your channels and the point where you use them for the beamforming, right? So you could kind of get around the channel aging problem in a very neat way. So in general, I find full duplex extremely fascinating as a technology, and I think this use case where measuring channel state information at the same time as you're using it for downlink beamforming and transmission, that's to me, that's the most convincing use case. Then whether we'll see this or when we'll see it is difficult to predict. I mean, I would not be surprised if one day we'll have it implemented in wireless access points, probably for that purpose that I mentioned. I mean, to get channel state information in, like, air quotes, real time.
Yeah.
What do you think, Emil?
I think for this thing we talked about earlier with localization and sensing, this could be useful as well, because then you transmit and you can also listen back on the radar signals. So
like a monostatic.
Becomes monostatic radar, and not bistatic. And I think one can definitely build this already, and it might be closer to put it on the base stations than have it in the user device, because if it requires a lot of extra hardware components, maybe we don't want it in a compact user device. So I've seen a lot of work also considering like a full duplex base station, and then users that are using either uplink or downlink, and you can handle more traffic, I suppose.
Yeah. Wow. Okay, great. So I think these were all the 10 questions.
Yeah, thank you very much to all the listeners for asking them. I hope they feel that we have actually answered it relatively well, at least. And please continue asking questions when we are putting out videos, and we try to respond to them either in episodes or in YouTube comments. I think YouTube is the best place to ask questions on particular the videos.
Absolutely, and don't forget to log into YouTube and like and subscribe us there. So then, thank you very much.
Thank you, and Happy New Year.
Bye.
Bye-bye.